Suppose f is from x to y and g is from y to z are both 1 to 1 and onto. Prove that g of f all inverse exists and that g of f all inverse is f inverse composed with g inverse. Now we're going to do both of these at the same time. Really, so to do this, we have to show that these two functions are the same. That meaning that if we plug one element into one function, we get the same result as if we plug that same element into the other function. Now, g of f is a function that sends elements from the domain of x to the codomain of g. So this is from x to z, which also means then that g of f inverse would be a function from z to x. Similarly, f inverse composed with g inverse would be a function from the domain of g inverse, which is z, to the codomain of f inverse, which is x. So these have the same domain and codomain, but what's really important here is the domain of both of these functions here. The domain of both of these functions is z. So the first thing we're going to do is we're going to take an arbitrary element from that set z. Now, since g is onto, then there exists an element y in the set y such that g of y equals lowercase z here. Now, since y is in the set y and f is also onto, they're both 1 to 1 and onto, then there exists an x in the set x from the domain of f such that f of x is y. And so here we have f of x equals y, g of y equals z. That means that g of f of x is z. Now put another way, we could say g of f of x equals z. Now this is where things get interesting. According to theorem 7.3.3, if f is a function from x to y and g is a function from y to z are both 1 to 1 functions, which in this case, that's exactly what f and g are. They're functions from x to y and from y to z that are both 1 to 1. Then the composition is 1 to 1. So that means that this composition function is 1 to 1. That just means that x is the pre-image of z. If this composition is 1 to 1, then that means that the pre-image has to be unique. That if z is an output of this composition, then z has to be a unique output, meaning that x is the only element that's mapped to z, meaning x is the only pre-image of z. So what we've shown so far is that when we plug z into the left-hand side, we get this element x specifically as the output of plugging z into that function. Now we need to show that if we plug z into this function on the right, that we also get the same x. So now let's consider f inverse composed with g inverse of z. And remember that g of y equals z. G is a 1 to 1 and onto function, so y is the only input that's mapped to z with the function g. Now since g is 1 to 1, then that means that y is g inverse of z. So y is the only pre-image of z. So that then means that f inverse of g inverse of z, which is really just f inverse of g inverse of z, this is really just f inverse of y, since g inverse of z is y. Now earlier we said f of x equals y, so since f of x equals y and f is 1 to 1, then that means that x equals f inverse of y. X is the only pre-image of y via the function f. So then we can say that f inverse of g inverse of z is really f inverse of y, which is really x. Notice we get x when plugging z into the right function, as when we plug in z into the left function, we also get x. Either way, we get x. And so these functions have to be equal to each other. Now, why does this inverse function exist? Keep in mind that the composition of 1 to 1 functions is 1 to 1. So if f is 1 to 1 and g is 1 to 1, then g of f is 1 to 1, which means that g of f inverse exists. Thanks everyone, and I'll see you in the next video.